Okay. So let's have a look at some of questions. These are so easy, so no need now. Maybe let's have a look at question 2.1. So it wants you to find the velocity at any time. So what you can get from the question is you can find the acceleration. Okay. So you express the acceleration in terms of vector, and then you know FU and MA, so you can get the acceleration to be this one. So how can you get the velocity from the acceleration? Hello.
You integrate it.
So you integrate once. It starts at rest. So most probably, first of all, you need to add an integral constant. So let's integrate this one. Okay. Most probably, you should add an integral constant. But if you start until the time you 0, right, then the C will be 0 also. Okay, so there's no disintegrating factor. So also for the position, you just need to integrate it once again, then you can get the answer. So don't need to do it. Okay.
Yeah.
So let's have a look at some other question. Like the question 2.4. It is relating the circular motion and the gravitational force. There are actually you can consider the F2 as the gravitational force. And you should also know that these two objects will rotate about its center mass.
Yes.
And then if they have the separation R, then you can use either one object to relate one equation. So let's say if I use the small m, then the net force is F equal to the small m times the acceleration. So that is R times omega squared. So R is the distance here. And then you just need to use the ratio, or you can, you know the ratio is big M to small m. Yeah. Right? Okay, I think you can solve this equation already. Yeah. Okay, easy question. 2.7. So find the constraint relating the vertical acceleration with the horizontal.
Oh. So I treat it as the acceleration along the rod is the same.
Yeah. So you can just make use of that property to do this question.
Okay.
So actually you can express the angle theta in terms of B and L. Okay.
Yeah.
Then you can get AY times cosine theta equal to AX times sine theta. Or we can do it in another way. Okay. Let's say this is acceleration A. Now this is have the length A. Then AX can be expressed as A dot dot. And AY can be expressed as B dot dot. But if you express AY as a B dot dot, that means if it is pointing upwards, it should be positive. If it is pointing downwards, it will be negative. So it depends on Because if you write down this equation, that means you assume AY and AX are all positive. And then you have already assumed that AY is point downwards. So I would rather you put a negative B dot dot here.
Okay.
So, and then one equation relating the A and B is the Pythagoras theorem. So what we can do next, we just differentiate ones first. Okay. Obviously, we need to differentiate twice to get the A dot dot or B dot dot. Okay, so we need to differentiate once more. But first of all, we can cancel out the 2. So let's try to differentiate once more. When you differentiate once more, then you should use the product rule. Okay, so how could you relate the A dot dot and B dot dot using these two equations?
Wait, AX is just A dot dot, right?
Yeah.
So can you just substitute it in because B dot dot equals to A dot dot times A over B, or
So what you say is A dot equal to negative B over A times B dot, and then you substitute in this formula.
yes.
And yes. So let's see if we can get the same answer.
Okay.
I think it's quite complicated in this question. If we do it like this one. Okay.
Okay.
And if you write it like this, you can see that actually the answer is not like this one.
Oh.
The reason behind it is that if it is rotating, actually there's another term similar to the centripetalization, and this law does not apply actually.
Oh.
But in most of the cases, it still applies if the object is moving in a translation motion. So if the relation is look like this one, you will rather to find the relation between the assertion using the geometry, and then you differentiate. Okay, using geometry and then you differentiate.
Okay.
So for part B, now suppose each rod, each end carries a positive mass m.
Mm.
That means in this case, you need to solve this equation. And it told you that it is initial at rest. So actually, if looking at this formula, you don't have this term.
Yes.
So you have this relation, and then you can draw all the free body diagram. The tension along the string, so the tension along the rod is along the rod. Okay, the tension is along the rod.
Mm-hmm.
Also, there is a non-motion here, and then there's tension along the rod.
Mm.
Mm. Yeah. Mm-hmm. And then if you write down two, and then you can write down another equation relating the tension and also the vertical and horizontal assertion, and that's it. You can solve these equations.
Okay.
Yeah. Okay. The next one is this case the pulley system is really not a common topic, but this is the topic that you really need to know how to do it.
Okay. Okay.
So the main problem is how you let the displacement or the distance and how you relate the assertion together. Or what variable will you let in this example? Mhm. What variable will you let in this example? Now, if that um, a more natural way to do it, or um, the method that you get less error is that you let if you see there's a vertical part of the string you let one variable for it. So let's say this one is x1, okay? So quite natural, you let it to be x1, and then maybe you let it to be x2,
Okay.
and one is x3. Now you can see that I will also put I don't know, a stroke here to represent the origin or the zero point of that variable, such that uh, later on that means you have let the direction of the variable already, and then this is x2. So how will you let another variable? Actually, for this one, you can let it to be downwards or upwards. It doesn't matter actually.
Okay.
Mm-hmm. So and then there's some constraint about the string. So that is x1 plus x3 is constant.
Mm-hmm.
And then x2 plus x4 is constant.
Yes.
So the assertion of m1 is so easy. It should be x1 dot dot. Mm-hmm. So how about the assertion of m2?
Is it x?
Mm.
Wait. X2 is actually 2x1, right?
x2 is equal to 2x1. No, the length of the string are not. The length of the two strings are not equal, related together. But you can say that x3 plus x4 is constant. Now what you can do, you should look at the diagram, and then you should take a distance or the displacement or the position vector of M2 from a fixed point.
Okay.
Where is a fixed point? This one is a fixed point. This one is not a fixed point because this pulley will move.
Pick the thing on the ground, like the.
Yeah, you measure the position vector of M2 object from this point to the M2. So then that should be the length x2 plus x3.
Oh, okay.
So that means the acceleration of M2 should be x2 dot dot plus x3 dot dot.
Okay, okay.
And then what you can do you need to relate these variables together. So what you can do, you differentiate these two equations. So then right now you have the relation between x1 and x3. So that means you can write A2 to be x2 dot dot minus x1 dot dot.
Okay.
Then right now you have just two variables in the acceleration, and then you have two equations.
Mm-hmm.
Right, but two equations are not enough to solve three variables. So there's another variable, that is the tension. So for M1 object, okay, because we have let downwards to be positive, so you need to for the force equation, you need to use M1G minus tension. That will be equal to M1 times A1.
Mm-hmm.
So similar for M2, okay? So that's M2G minus tension equal to M2 times A2.
Mm-hmm.
Do you notice any mistake in this equation about the tension?
Wait, is it like they're not necessarily equal?
And actually, they are not equal.
Oh, okay.
If you look at this pulley, so there are two tension downwards and one tension upwards.
Yes.
You let this tension to be theta, then this two should be theta2.
Yeah. Okay.
You may argue that why the forces of the pulley is balanced, because in most of question we assume that the pulley is massless. That means the net force of the pulley is always zero, no matter how large is the acceleration. Such that so you need to change this one to be two, and then the problem comes. We have just two equations, but we have three unknowns in these two equations. The tension is an unknown, x1 dot dot and x2 dot dot are also unknown. So what happens?
Like you relate x2 and x1, right? Like
So you need to write down one more equation to relate this distance. So actually, if you look at the graph, x3 plus x4 is also a constant.
yes. So yes, I see now.
And then let me see if I can relate them easily, okay? So there are three equations here. There are three constraint equations. And then x3, you can put it here, okay? So you get x1 dot dot equal to x4 dot dot.
Oh yeah, so
That means
x dot
one
equal.
will be
Yeah.
equal to negative x2 dot dot.
Yeah.
Okay.
Okay.
And then for this equation, that means you can write it down as negative x1 dot dot. Negative 2x1 dot dot.
Mhm.
That's it.
Yeah.
Oh, okay. You can take the screenshot. Okay. Oh, clear the screen now. Have you taken the screenshot?
Yes.
Okay. So and then next, for these two Pulley questions, when you do it by yourself now, you try to solve these two Pulley questions. So then let's go on. Have you still remember we have done this question already? This one. And
Oh, is it? Can you teach me again? I kind of forgot. Is it
oh,
like?
actually, if you have drawn the field diagram correctly, then you can solve this easily. So there are two tension here. And
Yeah.
tension. This is small m and big M.
Oh, okay.
So and then yeah, then you can solve there's only one variable, that is the tension.
Yes.
And let's have a look. 2.15. In this question, you definitely need to write down the equation like in you really need to use the assertion in this form.
Wait, is this disk horizontal or vertical?
Which one? This is a horizontal disk.
Oh.
So maybe let's let this distance to be RB.
Yes.
So if you look at the assertion at the R head direction, both of them will have a constant acting on it.
Yes.
And then the tension is along the negative R head position. So for the force equation of MA, so that should be the net force is negative T along the R head position direction. That's MA times RA dot dot and minus RA times omega square.
Uh.
Any question here?
Oh, you just substitute. Okay. Yeah.
Then you need to make use of the constraint. The RA plus RB equal to L, that is a constant.
Yes.
And then you can solve the equation not difficult. So this is negative RAB. Okay, if you put a positive sign on the whole equation, then you can add these two equations together. So then the answer is look like this one.
Should be minus, right? Is it
Where?
MBRB minus MARA,
Oh,
right?
I multiple the left one on both sides.
Oh, okay.
Okay, no question.
No question.
So then let's go on. The next chapter is also about the force equation, but it will be a little bit more difficult.
Oh, okay.
Let's have a look. The questions are so similar to each other. Oh, this one. I think they have solved this equation already. This question. Have they?
I don't remember. I think,
Maybe let's have a look at this question.
yeah. Oh, this is an equilibrium, right? So I just,
Yeah. This is in equilibrium.
okay.
Okay. I think you have looked at the question already. Actually, this question is quite similar to one question we have done before. If you still remember, there's one question in the static.
Yeah. Oh, yeah, yeah. The chain, yeah.
Yeah. So actually, this question we are using, although this one is a similar, it's not a count. So we are using a similar technique to solve this question. So what we need to do that? Actually, if you look at this answer, it's so difficult for you to think about one way to get the exponential here.
Yeah.
So what we need to do, like we need to cut it into very small part.
Oh, okay.
Mm, uh, which force is larger, TB or TA?
TA is larger, right?
Yeah, TA is larger than TB.
Yeah.
So if you take, so then let's draw the free ball diagram about this small arc. Okay, so can you draw the force on the graph about?
Okay. So
Mhm. So we like to try. You can't say this tension to be TB and TA because they are not equal to the tension at the end. How?
yeah. So
Okay. So what you need to do, maybe you let it to be T, and then because uh, the tension are not equal on both sides. So what you can let it, if you let it to be T, and then you can let this one to be T plus delta T.
okay.
And then for each small parcel, the tension has been increased by delta T. And then the concept is that you chop down into many small parts. And after that, you summation the change in each small part, such that you get the total change in the tension, TB and TA.
Okay. So
So can you relay some formula? Also, you should know that the angle here, you should let it to be delta theta. So could you relate the delta t and the delta theta together?
Wait, do I just use like, for example, here,
Mhm.
and then this is
Mm.
delta theta divided by 2.
Yeah.
So
You may also remember this formula, okay?
oh yeah, so
For angle approximation. And you divide all the forces in the horizontal component and the vertical component. And you can try to solve this equation.
okay. So
Mm-hmm. Uh, mm. So you almost get correct. So for cosine theta, you can approximate to be 1, or even you may need some time to approximate to be 1 minus the square root of 2.
okay. So
So you almost get the answer. So for these two equations, you need to simplify it more. So
yeah,
the first one, you can cancel out the t cosine theta over 2 on both sides.
yes.
And then what you left is f equal to del t.
Yeah.
Wow. On the next equation, you can simplify these two together. You get t theta, t d theta, or t del theta, or del t times del theta 2 equal to r. And yeah, this is equal to mu r. Yeah. And then what you need to take also, these two are small terms. So if they are multiple together, and you can see this is a small term here also, but we call
Yes.
it as a first order small term. This is second order small term. Then we can ignore this one and put it to be zero.
Okay. So
So actually, you can get through a simple equation. So that is dt equal to mu times r, okay? And then the second equation, what you get is t times d theta that equal to r. So see if you can get this, solve this.
oh, you're relating t and theta, right?
Yeah.
Okay. So
Yeah, you integrate on both sides, and then remember when you do the integration, it's much better for you to take it the definite integral. So
oh, okay.
so you put in the range of the integral. Otherwise, you need to solve the in arbitrary constant in the equation, and then they will be quite complicated. So it's TB, TA to TB, okay? TB to TA.
Oh, okay.
More than TA. Then you can get natural log TA divided by TB equal to mu times theta. Okay. This one is a very typical question. Any question? No?
No.
And then you capture the screen and then we go on.
Okay.
Look at 3.13. Now, you can see the question and ask told you that this is no need to solve the equation. That means this is not a really simple algebraic equation. Most probably, it is a calculus. You need to use the integration. or even it may be ODE. So do you understand why the question may need to use the integration?
Do you also divide it into small parts?
Yeah, but why you need to do so?
Mm, you want to find out the relationship between V and D theta, right? Or
Yes, but if you look at the question we done before about the forces or the except this one, okay, except this one. Like the questions we have done before, right? We don't need to use integration or differentiation. But in this question, we need to use it because one variable is not a constant. If everything is constant, then that's fine. You don't need to use integration. But in this case, one variable will depends on the angle theta. Of course, the speed will depends on it. And one very important variable is the acceleration. Acceleration also depends on theta. Can you see why?
is it the centripetal plus the rotational? It's like different.
Okay, maybe let's draw the feedback diagram first. So we can see the feedback diagram, there are two forces. The one is inertia and also the weight, and also the friction.
Oh yeah, there's friction. Yeah.
So can you find the magnitude of the non-Russian?
It's just
Now this one is not equal to mg cosine theta.
it's just mv squared over r, right?
Similar. The net force towards the center is n minus mg cosine theta. Then that equal to m v. Let it to be u. Okay, that will
Okay.
be v square of r.
Yeah.
I would prefer to write every variable in terms of theta. So I would rather use mr theta dot square.
Oh, okay.
Otherwise, you may think that v is not related to theta. Then, so this one can keep remind you that this one is a ODE.
Mhm.
So and then another equation is about the tangential component. Then that is the friction. So friction that equal to mu times n. So that equal to m times what? Keep remind you, you need to use this equation, yeah. Especially for the question relating to the uh, related to the circular motion. You really need to use this one.
Hmm.
So what do you think about this one?
Just put the wait. Actually,
For the R hat component, we have written down the equation already here.
yes.
That means this part is the tangential component. So what should be the acceleration here? Okay, you just have a look at the formula. Then what should be assertion? Sorry, I missed one component. I missed the weight component in the formula. Do you find it? So that should be the friction of
Yes.
mu times n plus the mg sine theta,
Oh, yeah.
m times assertion. So what should be assertion in this case?
Mm.
You can copy it down, okay? 2r dot theta dot plus r theta dot, is it?
Oh, you just,
Yeah, but you know the r dot is 0 in this case because the
uh,
r is constant.
yes.
One should be r, the big R times theta dot square, theta dot. Mm. But
Oh, okay.
actually, this one is wrong. Some small mistake in this question, in this part, in this equation.
Uh,
It's about the direction. Do you remember where does the fair head point to?
like up, right?
Like,
To
like
the up, right? Yeah.
yeah. So that points to the direction where the angle is increasing.
Yes.
This is our head component. So if you put it like this, that means the net force is along the fair head direction. So either you need to put a negative sign here. Okay.
Okay.
And then the next step, what you need to do is substitute the normalization into this equation.
Mm-hmm.
And then so-called you try to solve it, but you don't no need to solve it. I think this equation cannot be solved. It may not be able to solve.
Mm. Okay.
Okay.
Yeah.
So you can capture screen and then let's go on. So one you can just remind yourself, you may always need to use this equation in the in this chapter.
Mm.
So let's go on. Tunnel through the earth. I think this one is about the SHM.
Oh, okay.
We have done that question already. Off-center tunnel, we have done that question also. This is just SHM. Mm-hmm. We have done this question also. Yeah. Actually, I combined two similar questions together to form one question. Mm. So let's have a look at this one. This one. Uh, okay, this one is a horizontal circle. This is a horizontal circle. So may you try to write down the ODE first. So and then we can solve it together. So your turn to do this question. Mm. The equation of this one is quite similar to the one in the one we have done before, but this one will be much more easier because only the non-Russian. There are only two forces that you need to take care about. One is the non-motion towards the center, another one is the friction. And obviously, this question is much easier because you can solve it. So maybe let me to write down some equation. So yeah, similar, you need to use this concept. You in this question, and then the non-Russian will be equal to m times, because they want you to use the coefficient v. So let me, it depends on what you think. Maybe solve, we use the theta to solve it first, okay? So that equal to ml times theta dot square. That is a non-Russian. Then for the second part for the assertion, that is negative mu n equal to ml theta dot dot. You get the same equation. See? Hello, hello.
Oh, yeah.
Oh, do you know how to solve this equation?
Yeah, I can.
Mm.
Oh.
Mm,
Wait, sorry.
mm, mhm. So this one actually, this is you can consider it as a first order differential equation. It's
Oh,
in second order. Yeah.
oh,
If you consider to second order, it will be quite complicated. And this one is actually a separable differential equation. Now you can solve it like this one. Mhm. I think it's quite natural to solve it like this one.
yeah.
Then you integrate on both sides. Uh, so you may also do the uh, uh,
Definitely.
integral, yeah, from 0 to t. Mm, Okay,
Okay.
so we have find the fair dot in terms of t. So that means that then we get the velocity. Okay.
Okay.
So it should be somehow similar to so complicated. 1 over sorry L divided by mu t plus L divided by L naught. Okay. So let's have a look at part B. So what you can get the position, you just integrate once, so you can get the distance. Mm. Or actually, for the position, it's better for you to express in terms of the angle. So for you can just integrate this uh, once, and then can get the angle expressed in terms of t. Okay, I think this one is a natural or something. The answer should be. So if no question, then let's go on to the next. Okay, so I clear the screen now.
Yeah.
Mm. So, and for this question is so similar to what we have done before. And this is a differential equation. I think this one may be a little bit, maybe a little bit more difficult. Let me try to do it. Oh, but there only one force acting on the object. That means the net force should be negative B E times AV equal to M times the acceleration. Okay. Then you just need to integrate it once and then you can get. This is a separable differential equation.
Oh, yeah, yeah.
This is a separable differential equation. Okay. It's not difficult to get the answer. We will try to do it later on.
Okay.
Yeah, okay, we finish the question here. Okay, we finish the questions here. Now, the commission will not have one question maybe specific for, I mean the session test may not have one question that is uh, only on forces. So, but you need to know these techniques to do the question.
Okay.
So if the question is specific for force, then most probably this is a question about the dynamics, the rocket motion problem. That means uh, the force on a changing mass system.
Okay.
That one is much more difficult. Then let's have a look at the questions on chapter 4. The double integral starts in this chapter. Uh, just what we have done before. Now, actually, we have teach you how to find the center mass using the summation notation.
Mm.
Then how we can change the summation notation into integration. Now, actually, in mathematics, this one can be transformed into the integral. So, like you know for the integral, there is something delta d something, dx, dy, d something. So you need to consider which one should be in this part. So actually, the r is not a small component. The m is a very small component. What do I mean? For a rigid body or for an object, you need to cut into very small parts. And for this small parts, this is a delta m.
Yes.
And then this is position vector Ri. Then you take the summation of each small part together. So in this equation, actually, the most proper way to write it down is like this one, delta mi divided by summation delta mi. Then you need to change the summation sign into integral. Then the formula will look like this one. So, and then we can have a look how we can make use of this formula to do the question 4.1. 4.1, this is just a rod. That means this is one dimension only. So then we can write down the formula, this one. They have given you the lambda, that is the mass per unit length. So that actually, that means that dm over dx. The mass per length. Now the lambda depends on x. It depends on the position of the particle. So first of all, let's find the mass of the m of the rod. So that means this part, okay? So the total mass of the rod should be, you need to integrate the m. So let's draw the coordinate system first. So this is x-axis from 0 to L. Here is a rod. And then you need to cut the rod into very small parts. And this one is dm. It has a mass dm. So you say the coordinates of this small mass is from x to x plus dx.
Yes.
That means the length here, it is dx.
Yes.
And dm and dx is related together by the lambda. So that if you want to find the summation of dm, that equal to lambda times dx. And then you put the lambda inside this integral. And for the range of this integral, it's obviously that is the range of the x. That means it's from 0 to L. That's it. That's it. That's it. That's it. That's it.
Yeah.
Yeah. The remaining is left for you, okay, for finding the mass, okay. So skip it first. So, and then for part B, if you want to find the center mass, the x component of the center mass. So what you need to do, after you have got this, the total mass. So what you need to do is put the dm in the numerator, and then you integrate once.
Oh, okay.
Of course, this one is not that easy to do because you need to use the integration by part.
Yeah.
Then you can get the answer. So that's it for this question. Okay, you can take a screenshot. And I want to talk about the system with the varying mass next time, or maybe let's have a look at some of the question example in this chapter.
Okay.
Let's have a look. So let's have a look at this one. This one. Wow, it seems it's really a tough question. Do you understand this question? The question is not that seem easy to understand. Maybe you can have a look first.
Which diagram do you refer to? Is it the one at the bottom?
Yeah. The both pictures is describing the
Oh, the dike. Okay.
like one is the top view and one is the side view.
Okay, yeah. Wait, static pressure refers to
Static pressure refers to mgh, so the rho gh.
oh,
The static I don't know they have this term. So another one is a dynamic pressure. That means So when the water flow, when the water flow changes the direction, there should be a force acting on the water.
Oh, okay.
Yeah. The pressure due to that force in this question is called the dynamic pressure. So let's calculate the static pressure first. Obviously, the pressure is outwards. Okay, outwards.
Yes. So
I want to know if they just want to compare the pressure. Oh, they just compare the pressure. They are not comparing the friction. So by the pressure due to I think they compare the answer in terms of the variable h, variable h. They're not talking about the FH pressure. I think it's not. I think obviously for this part, the answer does not depend on h, but the pressure, the static pressure depends on h, and we know the answer for the pressure due to the water. That is depends on the depth of the water. That is pressure equal to rho gh. So that is a static part. So we can have a look at the answer, okay? Do you know this equation, rho gh?
yes.
So for the dynamic pressure, is related to the change in the momentum of the water. So you may, if you write down the formula, so that will be the force equal to del P over del T,
Yes.
but somehow you need to divide by the area. So you need to have a look at this
A is the area.
area to get the pressure.
Okay.
Maybe you could take a look, have a look at the question. The area here, the area A here, it means the area of the cross section of the water flow.
Okay.
That means the area, this area, okay, this area.
Yes.
We use the symbol A.
Oh, okay.
But for the pressure, you need to divide by the area here, okay, this length times the height.
Okay. Oh, so just R delta theta H.
Mm-hmm. Mm. This is the rate of change of momentum. That means it is the uh, the force.
Mm.
You need to use this one minus this one.
Oh.
So if you draw the graph, that means you can find the change in the momentum to be p dot times del theta. Okay, that means this one. Okay, this one. This is rho v squared times a times del theta, and rho av squared is a change in momentum. Do you understand why this one is a change in momentum?
No, I don't really understand.
Now the P momentum, the change in momentum, dP over dt, can be written as dm over dt times the velocity.
Yeah. So
But the velocity is constant, but then it can be written down as dm over d volume times the volume over dt.
yes.
This one is a density. This one equal to the cross-section area times velocity. The change over volume over the change in time.
Oh yeah.
So that equal to rho a v squared.
Yeah.
It's really fine because you may be the first time to look at this kind of question. So if you store more answer, okay, or the solution of the question in your brain, then next time you can solve these kind of questions.
Yeah.
Most of us experience this hard period because we haven't seen this type of question before. So it's not quite normal if you don't know how to do it the first time. So that's how we get the answer. But in this solution, if you're talking about the force, then the answer may be quite similar. But the pressure, the dynamic pressure does not depend on H. The slack pressure depends on H. So there may be some comparison. When you do the integration, when you're talking about the force ratio is not equal to this ratio. Okay. Because the dynamic pressure does not depend on the H. But the slack pressure depends on H. So if you're talking about the force ratio, this is not the answer. You can have a look here. So I told you that the dynamic pressure cannot be negated. It's not negligible. The ratio is around 0.22 for some values here. So then that's it. Next time we'll talk a little bit about the double integral or the triple integral. So we are solving some cases about semicircular disk hemisphere and circular shell.
Oh, so like multivariable.
Yeah, I think it's also in my note in the textbook that I've sent you before. Let me show you. Yeah, it's also in here. We'll talk about these cases next time. So try to solve the shell circular disk hemisphere. So any question for today? So we have lesson on next Tuesday, is it?
Yeah.
Okay, then see you next Tuesday.
Okay, see you.
Okay, bye bye.